When an enterprise ingests raw transactional data at high velocity, traditional computing architectures force those streams into a central physical hub. Eventually, the physics of processing that incoming volume on a single machine causes the entire system to throttle. Take a data engineering firm like Royal Research. When managing continuous, petabyte-scale unstructured data streams, relying on a centralized hardware node quickly becomes a severe operational liability. This diagram illustrates the failure of vertical scaling. You can purchase larger, more powerful server racks to increase compute power, but incoming data volume aggressively spikes past whatever physical ceiling you buy, mathematically outpacing the single machine. When that hardware threshold is breached, the downstream effects are immediate. Retailers cannot process purchasing patterns, hospitals face severe archiving delays, and autonomous vehicles drop sensor streams. Surviving this petabyte-scale ingestion requires abandoning the centralized hardware model entirely. Instead, the architecture has to physically distribute the load. Apache Hadoop provides that distributed computing paradigm. Originally built to handle web-scale indexing, it operates as a distributed framework for massive datasets. The core operating philosophy relies on decoupling storage from compute. Instead of forcing data into a central processor, workloads are distributed across a wide cluster of standard, commercially available servers. To execute this, the platform relies on three distinct pillars: HDFS to manage the distributed storage, MapReduce to handle the parallel processing, and Yarn to negotiate resources across the cluster. By isolating storage and processing onto separate layers, organizations gain the structural bedrock required to build massive enterprise data lakes and train heavy AI pipelines. Analytical. This diagram represents a baseline infrastructure for Royal Research, utilizing a flat network grid of commodity servers. The Hadoop Distributed File System, or HDFS, splinters large unstructured files into uniform geometric blocks, typically 128 megabytes each. Rather than storing the file in one location, these individual data blocks scatter and embed themselves evenly across the decentralized server grid. To prevent data loss if a single server crashes, HDFS automatically runs replication lines, creating two identical copies of each block on adjacent nodes. Storing raw, unstructured data in its native format across a decentralized cluster creates what is known as a data lake. In the healthcare industry, a single hospital network ingests millions of distinct patient records, high-resolution MRI scans, and massive genomic research files daily. HDFS handles this ingestion flawlessly because it does not require the data to be formatted or structured prior to storage. The raw medical files are simply shattered, scattered, and replicated. Distributing raw storage uniformly across a wide grid mathematically eliminates the single point of failure for an enterprise like Royal Research. If one server goes down, the cluster simply retrieves the replicated block from another node. Here we see the problem with traditional queries. They pull massive data blocks from the outer edges of the storage grid back into a central CPU. Hauling petabytes of data across a network creates crippling latency. MapReduce applies an inverse logic. Instead of bringing the data to the algorithm, it packages the algorithm and sends it directly to the data. During the map phase, the network transit drops to near zero. Local servers process their specific piece of the data block simultaneously, without sending anything across the wider network. In the reduced phase, the local nodes aggregate their findings and return only the minimal processed results to the central hub. This local processing model is highly effective for financial services managing institutional risk. To perform real-time risk assessments, banks have to analyze a sprawling matrix of market data, customer profiles, and credit histories. Processing that analysis locally on the storage nodes allows institutions to generate accurate threat models in minutes instead of days. Moving the compute payload directly to the storage layer resolves the network bandwidth bottleneck. The heavy data never travels. While MapReduce handles batch processing effectively, locking an entire enterprise cluster to a single processing engine is an operational bottleneck in itself. Breaking this lock requires a dedicated resource management layer. This is the role of Yarn, yet another resource negotiator. Yarn acts as the central control plane. As we see here, it dynamically tracks available CPU and RAM across thousands of grid nodes, allocating compute power exactly where it is needed, based on the incoming workload. By managing the resources independently of the processing engine, Yarn allows the cluster to run multiple distinct applications simultaneously without conflict. Decoupling resource management from processing allows a single cluster to act as a multi-tenant platform. The finance department can run a risk analysis batch job while the marketing team simultaneously queries customer data, all on the same physical hardware. This multi-tenant capability allows organizations to run advanced non-native computational frameworks like Apache Spark and Apache Flink. These external frameworks bypass MapReduce entirely. Instead, they operate by plugging directly into Yarn for resource allocation and pulling data directly from the HDFS blocks below. The development of autonomous vehicles provides a clear view of how this ecosystem functions in production. A test fleet generates massive volumes of raw environmental data from cameras, LiDAR, and radar arrays. This data lands continuously in the HDFS layer. The autonomous vehicle captures immense continuous volumetric geometry, building a precise digital twin as it moves through complex physical environments. To make sense of this geometry, companies route Apache Spark through Yarn to process the colossal HDFS repository, training the complex machine learning models that enable vehicle navigation. As the AI training data requirements expand, the Hadoop cluster scales seamlessly. Organizations add standard commodity nodes to increase capacity without sacrificing processing speed. Without the distributed storage and orchestration bedrock provided by Hadoop, deploying these heavy machine learning applications at an enterprise scale is computationally impossible. Despite its scalability, Hadoop is structurally optimized for massive batch processing, not millisecond real-time streaming. Modern architectures solve this limitation by integrating real-time streaming tools. As shown here, a platform like Apache Kafka buffers high-speed incoming data streams, dropping massive, consolidated data payloads into the HDFS block grid at scheduled intervals. Organizations also balance Hadoop against fully cloud-based data solutions, which offer elastic scalability and heavily reduced infrastructure management overhead. Enterprises frequently adopt a hybrid approach. They maintain Hadoop clusters on-premise to lock in fixed costs for massive static datasets, while utilizing cloud instances to handle sudden spikes in elastic compute demand. Implementing Hadoop requires navigating strict operational challenges, from complex cluster configurations, tight security integrations, to retaining highly specialized engineering talent. Managing administrative complexity and hybrid tool integration dictates the success or failure of a modern data infrastructure rollout. Decoupling storage and compute provided the exact structural mechanism required to bypass the vertical scaling bottleneck. What began as a framework to manage web-scale search indexing evolved into the complex orchestration engine required for enterprise data lakes and dense machine learning pipelines. Organizations like Royal Research, alongside global leaders in finance, healthcare, and automotive manufacturing, rely on this precise framework to maintain their data operations. Even with the rapid expansion of native cloud tools, Apache Hadoop's distributed architecture provides the baseline mechanics for processing massive datasets, securing its position as a central component of modern data engineering.